Go then. RLC series circuit. Okay, what we're going to do first thing today is introduce the two frequency dependent components at the same time in the same circuit. So we're going to look at a circuit where we've got resistance, inductance and capacitance. Basically, let's put 24 volts, 10 ohms of resistance, 8 ohms of inductance, and 6 ohms worth of capacitance. You could be given it in farads. At the moment we're avoiding that calculation, and I'm giving you the impedance of the capacitor and inductor. So you're being given effectively XL and XC, at least the two of at this stage. Yeah. So you could say that the total impedance for this circuit is equal to the impedance of the resistor, ZR, plus the impedance of the inductor, ZL, plus the impedance of the capacitor, ZC, which we could write out as R, the resistance, plus XLJ, because for an inductor the angle associated with the impedance is plus 90 degrees, minus J. Yeah. And then the common term there is J, so we can take that outside some brackets and say it's equal to R plus XL minus XC J. So the imaginary part, the vertical part, is the difference between the inductive reactance and the capacitive reactance. What that means is if XL is greater than XC, the circuit is inductive overall. We draw the diagram, we'll see that in a minute. Okay, if XC is greater than XL, so is of whether what it is overall, i.e. will it show up as leading or lagging, will depend on the overall nature of the circuit. So if we look at the impedance phasor, what we've got is we've got resistance at 10 ohms, we've got XL at 8 ohms, got XC at 6 ohms. What we've got overall is the overall reactance in there, which is equal to XL minus XC. The difference between the two. So they work against opposites to each other. The overall impedance of this circuit comes from completing that parallelogram, and there is Z in there. And because XL is greater than XC here, it's above the line, and that circuit, although it's got a capacitor in it, that circuit will overall appear to be inductive in nature, with terms to whether you get a leading or lagging current. Okay, so that's what we're expecting, a circuit that appears to be overall inductive. We do our calculations. And remember that XL is equal to 2 pi times the inductance. XC is equal to 1 over 2 pi times the capacitance. So, if we were to change frequency, this phasor would all change. If we change it enough for XC to become greater than XL, that resultant phasor will move down below the line. We'll have a circuit that's overall capacitive. And think back to your filters. That's the action the filter's trying to use to either accept or reject particular frequencies. By the way, we'll come back to it a bit later, maybe even next week, but there's a special case when XL and XC are equal to each other. Have something called resonance. Okay? And in that case, the circuit is overall just resistive. You'll also see that series resonance is something you kind of try and avoid if you can with high voltage, high AC voltages certainly anyway. All right. So that's where we're heading with this calculation. So we can calculate ZT as being equal to R, which was 10 ohms, plus, we open our brackets, XL is 8 ohms, minus 6J. So that's 10 plus 2J ohms. Yeah, if we're going to calculate the current, we need that in what form? Convert into polar is easiest. Sorry? Certainly not 10 angle 0. 10.2 ohms, angle 11.3 degrees. Yep. So now we've got our impedance. We can say I is equal to E over ZT. And the voltage was 24 volts. No angle mentioned, so we make this must be 0 degrees divided by 10.2 angle 11.3 equals 24 over 10.2 is 2.35 amps, angle minus 11.3 degrees. Yeah. Okay. So, and then we could use that current to calculate other values and so on. So I'm going to give you a bit longer example to have a go at now. Spend about 20 minutes, half an hour on that. Okay. Everyone happy with that? Yeah? So you combine the two together in that overall formula for impedance. Oh, civil. Does that work? We know the circuit we're expecting from the diagram is overall inductive. We've got a lagging current in an inductive circuit. Current lags voltage. So, have a go at this one. Ohm resistor. Ohm inductor. 15 ohm capacitor. AC source of 60 volts. Calculate I. Put impedance in polar form. B. Total current. C. Voltages. VR. VL. And VC. These ones. D. Prove KVL is obeyed by that circuit. Okay. Nearly, I reckon. Yeah. Right, guys. What we got here? Total impedance ZT equal to what? Looking for the formula to start with. Yep. And right, I always maintain the more times you write the formula out, the more likely you are to commit it to memory when you need it. Yep. So do that, and then we put the numbers in, which were 5 plus 10 minus 15 J ohms, and then convert that to polar. What do we get? 7.07 ohms minus 45 degrees. Incidentally, you will lose marks in the exam if you miss the units out in the correct place there, and if the angle's in degrees, you leave the degrees symbol on. Okay? So, let's say 7.07 ohms, angle minus 45 degrees. Is that what you would expect for a circuit where capacitive reactance is bigger than inductive reactance? Yes. Okay, if we, like I said, you may well be expected to sketch a phasor diagram in the exam. So we'd have R in here, we'd have XC there. I'd expect you to show me that there's a size difference between the two, XL, and a resultant reactance in here, X, and we get an impedance in there, Z, and the angle is negative. Okay, it's not to scale because that's nothing like 45 degrees, but yeah, I mean what you might want actually, XL minus XC, the overall reactance. Yeah. Alright, so that would be what I'd expect for a phasor diagram for that. Yeah. So B, I is equal to, yeah, Ohm's law, E over ZT. Ohm's law will not be in the formula sheet, by the way. 60 angle 0 degrees divided by our calculated impedance, 7.07 angle minus 45. When you're in a calculation like that, you don't need to put the units in. That's the final answer that's got to have the units in. And the answer to that is, somebody? 8.49 amps, 45 degrees. No, but they just, I'm saying, when you're trying to do division, that's cluttering the thing up and you don't need them in there. All right. So, everybody happy with that? 8.49 amps, angle positive 45 degrees. Because this calculation here is 0 minus 45, so it changes to positive. And quite often, in a hurry, in the exam, under pressure, they're the kind of areas you go wrong, two negatives making a positive. Okay, we check that with civil. We know this circuit is overall capacitive from the phasor diagram. So is a leading current correct? Because that's leading, a positive angle. Capacitive circuit, current is ahead of or leads voltage. Yep, so that check works. Yeah, because the capacitance is bigger, overall this circuit's going to look capacitive and have a leading current that leads the voltage. Okay? C. V R is equal to Ohm's law, I times R. I was 8.49, angle 45, and the resistance 5 ohms. So that is 42.5, I'll take. .5, right? That's 4 or 5. It depends on how you've rounded your other figures, and whatever you've got within that is close enough. Volts, angle, 45 degrees. Yep. And that's resistance, so we've got a voltage that's in phase with the current. They've got the same angle. That's what you would expect. Yep. Always current and voltage for a resistor, the isolated current and voltage on that component only, going to be in phase with each other, both at 45 degrees. VL is I times equate XL. Yeah, the reactance. Back 8.49, angle 45 degrees, times 10, angle 90 degrees for an inductor. Again, you're expected to remember that. Nope. Jake, basic principles. Series circuit. One current goes through all of them. Yep. Same current for all of them. Voltage drop, yes. Okay. Remember, series circuit, current same, voltage is different. Parallel circuit, voltage is same, current's different. Alright. So we're gone. The answer to that is, must be 84.9, angle 135 degrees. Let's calculate your needed hopefully. And volts in there. Yeah. And if we check that with civil, a suggestion that the current is lagging behind and it's got a bigger angle. Sorry, it's got a smaller angle. Yeah, so it's behind. Alright, because we go round the circle that way. And current's at 45 degrees. And voltage is round here at 135 degrees. Yeah, so although there's no zero there, you can still look at whether the current's leading or lagging as a check. And lastly, VC is I times XC. It's 8.49, angle 45 degrees, times, we've got 15, angle minus 90 degrees. The answer you get there is, please, let's go 127 volts then, angle minus 45. Okay. In the inductive part of circuit, voltage is behind, there's a negative angle, current's a positive angle, so voltage is up behind or lagging the current, which is what you would expect. Okay. Now, if we looking at part D, KVL says E is equal to VR plus VL plus VC. Yeah? But if we add together 127, 84.9 and 42.5, we don't get 60 volts. Yeah? What we must do to prove the law is add them together in rectangular or in complex form, and the easy way is rectangular. So who's got the three voltages in rectangular form? For me, please. $30 plus $30J. Yep. $30 minus 60 is minus 30 plus 90 is 60. 30 plus 60 is 90, minus 90 is 0J. 30 plus or minus 0J volts. KVL proven. J terms cancel out, and the real parts equal 60 volts. Okay? All happy with that? Yeah? Right. Have a look at an RLC. That's really RL in parallel with C. So we're going to look at resistor and inductance in series in parallel with a capacitor connected to an AC source. So here we'll have a total current, and we'll have an IL with the inductor, and an IC with the capacitor. 5 ohm resistor, or the resistance to the inductor is 5 ohms, 10 ohms XL, and 15 ohms of capacitance. 60 volts. Again, no frequency needed because you've been given the reactances and not the component values. Alright, what I'm going to ask you to do is calculate the total impedance, ZT, code 4, B, total current I, C, currents, IL and IC, and D, prove Kirchhoff's current law this time. Yeah. Your best bet for calculating the total impedance, I'll just get you started on this. ZT is equal to, and you really need to use product over sum. So that's you're going to want the impedance of the resistor inductor in series multiplied by the impedance of the capacitor, and then down the bottom you'll have ZRL plus ZC. Yeah, so you can add them together easily at the bottom using rectangular form and get the bottom line. Yeah, you can if you convert to rect. Well, you've got them in rectangular form, haven't you? Because you've got XL and XC and R. Yeah. Because that bottom line is going to be R plus XL minus XCJ, isn't it? Yeah. Top line. If you convert these to polar, you can multiply them together, and then convert the bottom line, the denominator, after you're added it to polar, and then you can do the overall division. Alright, everybody comprehend that? So, add the bottom line together, rectangular form, convert it to polar, multiply the top line together in polar form, and then do the final division. Because of the complex number arithmetic. On the top line here, we've got ZRL, which is 5 plus 10J. We multiply that by ZC, which is 0 minus 15J. And then the bottom line is R, which is 5 ohms, plus L, which is 10J ohms, minus C, minus 15J. Yeah. So the way to tackle this, we want to multiply two complex numbers together as the numerator. So if we convert them to polar form, we get, what you should get is 11.2 angle 63.4 degrees for the 5 plus 10J, multiplying that by 15 angle minus 90 degrees. You know it's minus 90 because that's a capacitor. And then this bottom line is 5 plus 10 minus 15. There's 5 plus 5J. That's what that equals. Put that over here. Minus 5J, sorry. 5 minus 5J. When we convert that to polar form, we get 7.07 angle minus 45 degrees. Yeah. We're now going to, then when we multiply the numerator out, we end up with a fraction that consists of two polar numbers, 167.7 angle minus 26.6 degrees divided by our 7.07 angle minus 45 degrees. And now we've got two polar numbers, easy to divide. The result is that ZT is equal to 23.7 ohms angle 18.4 degrees. Yeah. So that's how you do that. Use the conversion between the two forms. So if you're adding together or subtracting, you use rectangular form. If you're multiplying or dividing, you want the numbers in polar form for the easiest method. Okay. So that's our total impedance. B. We can now find IT from E divided by ZT. That's 60 angle 0 divided by 23.7 angle 18.4. The result of that, Nathan, is (3.52 amps minus 18.4 degrees. So that is a total current flowing or being delivered by the source, this current here. Now, the voltage across the capacitor and the resistor inductor in series is the supply voltage, because they're in parallel. Voltage is the same, isn't it, Jake? Yeah. So C I L is equal to E divided by ZRL. That's 60 angle 0 degrees. Now we want the polar of R and L in series, which we have there at 11.2 angle 63.4 degrees. I've got 5.36 amps angle minus 63.4 degrees. So that's one current through the resistor and the inductor. IC is E over ZC. Call it IRL if you like. You'd represent a real inductor by a resistor and a capacitor in series anyway, so yeah. 60 angle 0 divided by, and the polar for the capacitor is ZC in polar form, 15 angle minus 90 degrees. Yep. So we got 4 amps angle plus 90 degrees. Yep. So we're looking for IL and IC. So part D, by Kirchhoff's current law, IL plus IC equals the total current. At the moment, our total current is 5 something amps, wasn't it? No, 2.52 amps. We add together 5.36 and 4, we certainly don't get 2.52. What we have to do is convert both of them to rectangular form. So IL, I've got 2.4 minus 4.79 J amps, and IC converted to rectangular, 0 plus 4J amps. Add those two together, you get 2.4 minus 0.79 J amps. Converting that back to polar form, I got 2.53 amps angle minus 18.2 degrees, which is close enough to what we had in the first place to confirm, allowing for rounding errors as we've gone through the total current. Sorry? That's right, you can eat current, but you can't eat amperages. Good old ohmage. Series resonance. Okay. Right. We already know XL is equal to 2 pi F times L. We can also use the angular frequency form of omega times L, where omega is equal to 2 pi F, and we know that XC is equal to 1 over 2 pi FC, or it's equal to 1 over omega C. So that facts we already know. At resonance, XL is equal to XC. So at a particular frequency, e.g. at a we'll call it FR, F resonance. So looking at these two, the top two formulae for XL and XC, if frequency is increasing, XL is getting bigger, but XC is getting smaller, which is what happens, then there'll be a point where they equal each other. That's, sorry? You experienced that in the filter. There's always one circuit where you see that and you get this spotted voltage. You'll understand a little bit more where that comes from when we look at resonance for an actual circuit. Yeah. So there's this point where, as frequency changes, the two reactive components become equal to each other. Okay. Now, if we look at that in terms of if at that resonant frequency XL is equal to XC, then we can say that omega resonance, resonant frequency, times L is equal to 1 over omega resonance times C. Alright, and then trying to get to a formula for omega R. What is the resonant frequency for two given component values? Alright, so what do I need to do to get omega R on its own? What's the first part of rearranging that formula to get both these two omega R's together and eventually on its own? Yeah, so multiply by omega R. So we end up with omega R squared times L is equal to 1 over C. Divide by L, we have omega R squared is equal to 1 over LC, and then square root both sides. Must do it to both. Yep. So we end up with omega R is equal to the square root of, we don't need square root 1, square root of 1 is 1, 1 over root LC. Yeah. So that's in omega form. If we want it in frequency in hertz form, we'd write omega resonance as, I'll do it in a different colour, 2 pi f is equal to 1 over root LC, and then we need to divide by 2 pi to get that over the other side. We end up with F resonance is equal to 1 over 2 pi root LC. So there's two forms for that formula to find the resonant frequency. One, if you use an omega, or the angular frequency. One, if you're using the frequency in hertz. Possibly. Yeah. Just depends on whether there's a question in the exam around resonance or not. But what isn't going to be in a formula sheet is the knowledge that resonance mean XL and XC are equal to each other. That needs to be committed to memory. Okay. What we'll do first up next week is look at a circuit that is experiencing resonance and see what happens in that circuit regarding the voltages. Alright? So, project